Hello class. Got another big one today. So today we're going to be talking about the second fundamental theorem of calculus and kind of what happens if you're dealing with variables as bounds. But because that can happen. You may be asking, Mr. B, what is the fundamental theorem of calculus? What is the first fundamental theorem of calculus? And I probably should have said this when I initially taught it, but the first fundamental theorem of calculus is that, like, unbounded integrals will give you antiderivatives, right? So this kind of gives you, like, a function like f of x, like big F of x, right? Where, you know, if you were to derive now f of x, big F of x, you get little f of x, right? And so this first fundamental theorem of calculus really shows that derivatives and integrals kind of go hand in hand, but are inverse operators. Now, the second fundamental theorem of calculus further exemplifies that derivatives and integrals are specifically like inverse and canceling operators. But first, we're going to talk a little bit about what it means if you have a variable in your bounds. Most of the time in real world applications, and even in like calculus applications, you'll see variables as an upper bound. For example, let's go with x. Actually, no, I'm feeling a bit spicy today. Let's go with t. T for time, and let's have our lower bound be 0, right? Now, let's say you're integrating, you're in a physics class. You're integrating some velocity function, right? Velocity of time with respect to time. Now, this is, we're going to adopt a couple notation things. First of all, I'm just going to give this like a little tick mark here. Let's call this like t prime. No, actually, let's not do that, because that kind of makes you think of like a derivative, right? Let's have, I don't know, let's have a little smiley face, right? D of dt smiley face, v of t smiley face, right? What this is trying to say is that this t smiley face and dt smiley face, they're just different variables from t, because what's going to end up happening is when we take this integral, we're going to get a function of t, but all these t smiley faces are going to go away. So this is what I like to call like a function of like a dummy variable. We set up this equation like this because eventually, as you see in the future, we're just going to get rid of it. And I guess I should note, remembering our video a very, very long time ago about how positions, velocities, and accelerations relate through derivatives, well, you know, if we have a position, let's say x of t, that goes to a velocity, if you differentiate, right, and an acceleration if you differentiate again. So derivative of position is velocity, derivative of velocity is acceleration. Fun fact, it goes the other way around too. The integral of acceleration is going to get you a velocity, and the integral of velocity is going to get you a position, right? And I find it really interesting that velocity is a really good example of this, because, like, think about this. You're integrating with, like, bounds, and it may, like, seem conceptually weird, but just think of it in terms of positions and velocities. If you're moving at 10 miles per hour for 10 hours, how far did you travel? Well, you traveled 100 miles, right? If you're traveling 10 miles per hour for 10 hours, right? That'd be very weird, but that integral would look something like this. It'd look like from 0 to 10 of 10 dx, right? And then that'd get that 10x from 0 to 10, and that just gets you 100, right? So I love positions, velocities, and accelerations as examples of calculus concepts. They fit very well. In this case, we're going to use it to show the second fundamental theorem of calculus in a bit, and we're going to show what happens when you have, like, variables, right? So this is going to equal to, and by that logic, the integral of this velocity is going to be equal to some position as a function of t, and then for now, smiley face. And now we're going to integrate that from 0 to t. Now, when we plug this in, we're going to get x of t minus x of 0. And this is like a very, very common thing if you do like physics or something like that, or engineering with like real applications of calculus. A lot of times you're going to be integrating from some t equals 0, I guess, or like t sub 0, this bottom bound is usually something to represent like an initial time or an initial position, initial velocity, right? In this case, I just had it from time equals 0 from equals to time, right? And what you might see is it's like, okay, g of x or g of t is some function, and this function is represented by an integral, right? And so, okay, let's say t is equal to 1. Okay, all of a sudden this bound just becomes 1. Now t is 100, this bound becomes 100. And so you see that a lot as well, right? In which case, this could be like x of 100 minus x of 0, right? And this x of 0 is it's a lot like a plus c. It's a lot like an initial condition, especially with like real examples. So, okay, enough with that quick interlude. To conclude, when you're dealing with variables in your bounds, you basically just do the same thing you do with constants in your bounds, with numbers in your bounds. You just simply plug them in, right? Now, it is important that you don't say like, okay, integral from like 0 to x of like f of x dx, because it's improper math notation to integrate a function with respect to x and then plug in x as a changing variable into that new function. It's just improper notation, and we generally don't do that. I know some teachers and professors will get mad at you if you do what I told you not to do just then. So I would adopt the dummy variable strategy where you just add like a little tick mark there, or draw a little smiley face or a star or something. Anything to signify it's a different variable. You could even give a different variable. I just like writing like t to match t and x to match x, because it like helps me tie the two together, that we're still dealing with time or position or something like that. Okay, big thing here. Second fundamental theorem of calculus. This is showing that derivatives and integrals are in fact inverse operations, right? So it's going to look something like this. d dx, that's going to signify our derivative of, and that's a parenthesis, an integral, let's say from 0 to x, or even 1 to x, you'll see why in a second, of some function f of x. I'm going to call this x star this time, dx star. So the derivative of this integral, what happens? The second fundamental theorem of calculus tells us that essentially the derivative goes away and the integral goes away. You keep your integrand though. This is going to be equal to f of x star, right? But we're going to plug in our bounds as normal, and then there's one extra fun step. It's going to be equal to f of x now minus f of 1. But because we did a derivative, we're going to have to remember a chain rule, which is weird to think about. And the proof behind this is kind of a lot, and I'm not going to show it because I think it's kind of beyond the scope of an introductory calculus class. I don't even believe I was taught this. It's not the worst thing in the world, right? So we're going to have a chain rule, right? We're going to take the chain on this x, and we're going to get times 1, or I guess I should say times 1 specifically for this portion here, right? So that's going to be times 1, so it doesn't even change. But then this here, the chain on this 1 is 0, right? And so this constant term actually just goes away. So the second fundamental theorem of calculus not only shows us that derivatives and integrals are inverse operations, but when you take the derivative of an integral, you're essentially just going to plug in variables of your plug in the variable bounds, and then the constant bounds just disappear. They magically vanish because of the chain rule. The chain rule is our best friend, right? And so, long story short, if you take the derivative of the integral of f of x, you just get f of x. So that's the simplest way I could put it. The derivative and the integral simply cancel. And you're only ever really going to see this with in like variable form, in which you have a variable in your upper or lower bound, or both. Right? And it's possible that you have in both. Not very common, but possible. In the case that they're both constants, think about it like this. If they're both constants, you're taking the derivative of some integral, just say like 0 to 1 of blah, 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 blah. It doesn't even matter because this integral is going to be an area, and that area is going to be some number. So you're taking the derivative of some number, and the derivative of any constant number is 0. That was a really bad 0. It is 0, right? So second fundamental theorem of calculus is pretty awesome, I'd say. Cool. So that's really it for all for this video. I don't have any, like, I would give you an example or another example, but it's really not that difficult. You can have, the only thing I will say that I'm not going to go over in this video is that you can have a variable in both bounds, in which case you still have to take the chain rule on both those bounds. And sometimes those bounds aren't just x. Sometimes that bound can be x squared, in which your chain rule might just be like 2x, right? And so you have to think about that. Don't forget the chain rule. You won't forget the chain rule ever. Maybe if I do something like funny, you will like remember this, and you'll remember to like not forget the chain rule. So like, don't forget the chain rule. All right, so see you later, class. Goodbye.